In the mathematical fields of differential geometry and tensor calculus, differential forms are an approach to multivariable calculus that is independent of coordinates. Differential forms provide a unified approach to defining integrands over curves, surfaces, volumes, and higher dimensional manifolds. The modern notion of differential forms was pioneered by Cartan. It has many applications, especially in geometry, topology and physics. For instance, the expression f dx from one-variable calculus is called a one-form, and can be integrated over an interval a, b, in the domain of f, and similarly the expression f dx dy plus g dx dz plus h dy dz is a two-form that has a surface integral over an oriented surface S. Likewise, a three-form f dx dy dz represents a volume element that can be integrated over a region of space. The algebra of differential forms is organized in a way that naturally reflects the orientation of the domain of integration. There is an operation D on differential forms known as the exterior derivative that, when acting on a k-form, produces a form. This operation extends the differential of a function, and the divergence and the curl of a vector field in an appropriate sense that makes the fundamental theorem of calculus, the divergence theorem, Green's theorem, and Stokes' theorem special cases of the same general result, known in this context also as the general Stokes theorem. In a deeper way, this theorem relates the topology of the domain of integration to the structure of the differential forms themselves. The precise connection is known as de Rham's theorem. The general setting for the study of differential forms is on a differentiable manifold. Differential one-forms are naturally dual to vector fields on a manifold, and the pairing between vector fields and one-forms is extended to arbitrary differential forms by the interior product. The algebra of differential forms along with the exterior derivative defined on it is preserved by the pullback under smooth functions between two manifolds. This feature allows geometrically invariant information to be moved from one space to another via the pullback, provided the information is expressed in terms of differential forms. As an example, the change of variables formula for integration becomes a simple statement that an integral is preserved under pullback. History. Differential forms are part of the field of differential geometry, influenced by linear algebra. Although the notion of a differential is quite old, the initial attempt at an algebraic organization of differential forms is usually credited to Cartan with reference to his 1899 paper, Concept. Differential forms provide an approach to multivariable calculus that is independent of coordinates. Integration. A differential form can be integrated over a manifold of the same dimension. A differential one-form can be thought of as measuring an infinitesimal length, or one-dimensional density. A differential two-form can be thought of as measuring an infinitesimal area, or two-dimensional density, and so on. A differential form is only well-defined on oriented manifolds. An example of a one-dimensional manifold is an interval a, b, and intervals can be given an orientation. They are positively oriented if a less than b, and negatively oriented otherwise. If a less than b, then the integral of the differential one-form f dx over the interval a, b is which is the negative of the integral of the same differential form over the same interval when equipped with the opposite orientation. That is, this gives a geometrical context to the conventions for one-dimensional integrals, that the sign changes when the orientation of the interval is reversed. A standard explanation of this in one-variable integration theory is that, when the limits of integration are in the opposite order, the increment dx is negative. The integrals are negatives of one another because the oriented lengths are opposites. More generally, an M-form is an oriented density that can be integrated over an m-dimensional oriented manifold. If M is an oriented m-dimensional manifold, and M is the same manifold with opposed orientation and omega is an M-form, then one has These conventions correspond to interpreting the integrand as a differential form, integrated over a chain. In measure theory, by contrast, one interprets the integrand as a function f with respect to a measure mu and integrates over a subset A. Without any notion of orientation, one writes to indicate integration over a subset A. This is a minor distinction in one dimension, but becomes subtler on higher dimensional manifolds. See below for details. Making the notion of an oriented density precise, and thus of a differential form, involves the exterior algebra. The basic one forms are the differentials of the coordinates. Each of these represents a covector that measures a small displacement in the corresponding coordinate direction. A general one form is a linear combination of these differentials where they are functions of the coordinates. A differential one form is integrated along an oriented curve as a line integral. The basic two forms are expressions, where I less than j. This represents an infinitesimal oriented square parallel to the plane. A general two form is a linear combination of these, and it is integrated just like a surface integral. A fundamental operation defined on differential forms is the wedge product. This is similar to the cross product from vector calculus, in that it is an alternating product. For instance, because the square whose first side is and second side is to be regarded as having the opposite orientation as the square whose first side is and whose second side is. The wedge product allows higher dimensional differential forms to be built out of lower dimensional ones, in much the same way that the cross product in vector calculus allows one to compute the area vector of a parallelogram from vectors pointing up the two sides. In addition to the wedge product, there is also the exterior derivative operator d. Like the differential of a function, the exterior derivative gives a way of quantifying sensitivity to change of a differential form. In Rn, if omega equals f dxa is a k-form, then d omega is defined by with extension to general k-forms occurring linearly. This more general approach allows for a more natural coordinate-free approach to integration on manifolds. It also allows for a natural generalization of the fundamental theorem of calculus. Differential calculus let U be an open set in Rn. A differential zero form is defined to be a smooth function f on U. If V is any vector in Rn, then f has a directional derivative Vf, which is another function on U whose value at a point Pu is the rate of change of f in the V direction. In particular, if V equals Ej is the jth coordinate vector, then Vf is the partial derivative of f with respect to the jth coordinate function, i.e., f xj, where x1, x2, xn are the coordinate functions on U. By their very definition, partial derivatives depend upon the choice of coordinates. If new coordinates y1, y2, yn are introduced, then the first idea leading to differential forms is the observation that Vf is a linear function of V, for any vectors v, w and any real number c. This linear map from Rn to R is denoted dfp and called the derivative of f at p. Thus dfp equals Vf. The object df can be viewed as a function on U, whose value at p is not a real number, but the linear map dfp. This is just the usual fresh A derivative, an example of a differential one form. Since any vector v is a linear combination Vj-Ej of its components, df is uniquely determined by dfp for each j in each Pu, which are just the partial derivatives of f on U. Thus df provides a way of encoding the partial derivatives of f. It can be decoded by noticing that the coordinates x1, x2, xn are themselves functions on U, and so define differential one forms dx1, dx2, dxn. Since xi, xj equals delta ij, the Kronecker delta function, it follows that the meaning of this expression is given by evaluating both sides at an arbitrary point p. On the right-hand side, the sum is defined pointwise, so that applying both sides to Ej, the result on each side is the jth partial derivative of f at p. since p and j were arbitrary. This proves the formula. More generally, for any smooth function xi and high on U, we define the differential one form alpha equals ig dhi point y's by for each pu. Any differential one form arises this way, and by using it follows that any differential one form alpha on U may be expressed in coordinates as for some smooth functions phi on U. The second idea leading to differential forms arises from the following question. Given a differential one form alpha on U, when does there exist a function f on U such that alpha equals df? The above expansion reduces this question to the search for a function f whose partial derivatives f g are equal to n given functions phi. For n greater than 1, such a function does not always exist. Any smooth function f satisfies, so it will be impossible to find such an f unless for all I and j. The skew symmetry of the left-hand side in I and j suggests introducing an antisymmetric product on differential unforms, the wedge product, so that these equations can be combined into a single condition where is defined so that this is an example of a differential two-form. This two-form is called the exterior derivative d alpha of alpha equals j equals 1 nfj dxj. It is given by, to summarize, d alpha equals 0 is a necessary condition for the existence of a function f with alpha equals df. Differential zero forms, one forms, and two forms are special cases of differential forms. For each k, there is a space of differential k-forms, which can be expressed in terms of the coordinates as for a collection of functions phi1 I2. Ik. Differential forms can be multiplied together using the wedge product, and for any differential k-form alpha, there is a differential form d alpha called the exterior derivative of alpha. Differential forms, the wedge product and the exterior derivative are independent of a choice of coordinates. Consequently, they may be defined on any smooth manifold M. One way to do this is cover M with coordinate charts and define a differential k-form on M to be a family of differential k-forms on each chart which agree on the overlaps. However, there are more intrinsic definitions which make the independence of coordinates manifest. Intrinsic definitions. Let M be a smooth manifold. A differential form of degree k is a smooth section of the kth exterior power of the cotangent bundle of M. At any point Pm, a k-form beta defines an alternating multilinear map, where Tpm is the tangent space to M at P. Equivalently, beta is a totally antisymmetric covariant tensor field of rank k. The set of all differential k-forms on a manifold M is a vector space, often denoted omega k. For example, a differential one-form alpha assigns to each point Pm a linear functional alpha p on Tpm. In the presence of an inner product on Tpm, alpha p may be represented as the inner product with a tangent vector xp. Differential one-forms are sometimes called covariant vector fields, covector fields, or dual vector fields, particularly within physics operations, as well as the addition and multiplication by scalar operations which arise from the vector space structure. There are several other standard operations defined on differential forms. The most important operations are the wedge product of two differential forms, the exterior derivative of a single differential form, the interior product of a differential form in a vector field, the Lie derivative of a differential form with respect to a vector field, and the covariant derivative of a differential form with respect to a vector field on a manifold with a defined connection. Wedge product. The wedge product of a k-form alpha and an L-form beta is a form denoted alpha lambda beta. For example, if k equals L equals 1, then alpha lambda beta is the two-form whose value at a point P is the alternating bilinear form defined by for v, WTPM. The wedge product is bilinear. For instance, if alpha, beta, and gamma are any differential forms, then it is skew-commutative, meaning that it satisfies a variant of anticommutativity that depends on the degrees of the forms. If alpha is a K-form and beta is an L-form, then Riemannian manifold on a Riemannian manifold, or more generally a pseudo-Riemannian manifold. Vector and covector fields can be identified, and additional operations can thus be defined, such as the Hodge star operator in codifferential, which is adjoint to the exterior differential D. Vector field structures on a pseudo-Riemannian manifold. One forms can be identified with vector fields. Vector fields have additional distinct algebraic structures, which are listed here for context and to avoid confusion. Firstly, each tangent space generates a Clifford algebra, where the product of a vector with itself is given by the value of a quadratic form, in this case, the natural one induced by the metric. This algebra is distinct from the exterior algebra of differential forms, which can be viewed as a Clifford algebra where the quadratic form vanishes. Clifford algebras are thus non-anti-commutative deformations of the exterior algebra. They are studied in geometric algebra. Another alternative is to consider vector fields as derivations, and consider the algebra of differential operators they generate, which is the WEYL algebra, and is a non-commutative deformation of the symmetric algebra in the vector fields. Exterior differential complex. One important property of the exterior derivative is that D2 equals 0. This means that the exterior derivative defines a cochain complex. By the Poincare lemma, this complex is locally exact except at omega 0. Its cohomology is the RHAM cohomology of M. Pullback. One of the main reasons the cotangent bundle rather than the tangent bundle is used in the construction of the exterior complex is that differential forms are capable of being pulled back by smooth maps, while vector fields cannot be pushed forward by smooth maps unless the map is, say, a diffeomorphism. The existence of pullback homomorphisms in der RHAM cohomology depends on the pullback of differential forms. Differential forms can be moved from one manifold to another using a smooth map. If Mn is smooth and omega is a smooth K-form on N, then there is a differential form F omega on M called the pullback of omega, which captures the behavior of omega as seen relative to F. To define the pullback, recall that the differential of F is a map F, trademark Tn. Fix a differential K-form omega on N, for a point P of M and tangent vectors V1, Vk to M at P. The pullback of omega is defined by the formula more abstractly. If omega is viewed as a section of the cotangent bundle Tn of N, then F omega is the section of Tn defined as the composite map. Pullback respects all of the basic operations on forms. The pullback of a form can also be written in coordinates. Assume that x1, xm are coordinates on M, that y1, yn are coordinates on N, and that these coordinate systems are related by the formulas y equals phi for all I. Then, locally on N, omega can be written as where, for each choice of I1, it is a real-valued function of y1, yn, using the linearity of pullback in its compatibility with wedge product. The pullback of omega has the formula each exterior derivative dFi can be expanded in terms of dx1, dxm. The resulting K-form can be written using Jacobian matrices. Here, stands for the determinant of the matrix whose entries are